CP2-2 is all about defining central and inscribed angles, as well as talking about the relationships that happen between chords, central angles, and arcs. So a quick review from yesterday: a central angle is an angle that has its vertex at the center of a circle. And its sides are radii. So it'll look something like this. And recall that that measure is the same as the measure of the arc. My inscribed angle is an angle that has its vertex on a circle, which means its sides are chords. So if my vertex is on a circle and I draw in some chords, that's my inscribed angle. And that angle is always half as big as the intercepted arc, so that the arc that is on the other end of that angle. So if we're doing an example, this angle is 47 degrees, and I'm looking for this arc to go from inscribed angle to arc. I just need to double my angle measurement. If I had my arc measurement and I was trying to find my angle, I would need to divide it by 2. So 47 doubled, 40 doubled is 80, 7 doubled is 14, so x is 94 degrees. A similar problem, this time I'm looking for x and y. This entire semicircle has to add up to 180 degrees. So just this arc BD has to be 78 degrees, because 180 minus 102 gives me 78. X is then half as big as 78. Half of 70 is 35. Half of 8 is 4. So x is 39 degrees. I'm going to follow that same process but backwards to figure out what y is. So 38 is half as big as the arc CE. 35 doubled gets me to 70, plus 3 doubled gets me to 76 degrees. CED is a semicircle. 180 minus 76 tells me that y has to be 104 degrees. You have this page on your notes as well, so if you click on the scissors, or if you have an updated notability, the letter T, you can drag and sort and double check that yours match mine. There's also a GeoGebra link in Schoology, and if you play with that a little bit, you'll start with a circle, and you'll see that there's 2 chords, and they're marked congruent, or they have the measurements there. Okay. So they're congruent. And then there's also angles from the ends of those chords to the middle. And as you move those around, you'll notice that those angles are always the same. So they're always congruent. And that the arcs on the outside of those angles, or the arcs that those angles define, are also congruent. So we can conclude that the central angles of congruent chords are congruent, and that their intercepted arcs, so the arcs on the outside, are always congruent. If we want to sound mathy about it, we can say that if 2 chords in a circle are congruent, then they determine 2 central angles that are congruent. And if 2 chords in a circle are congruent, then their intercepted arcs are congruent. So if I have a circle and I have 2 chords that are marked congruent, if I draw in angles there, those 2 angles will be the same, and the 2 arcs will be the same. So in this example, I'm told that both chords are 10, which means the arcs have to be the same as well. So 80 has to equal 4x. When I divide by 4 to isolate x is 20. In this example, we're again told that the two chords are the same. So I know right away that this piece will be 78. My entire circle adds up to 360. 360 minus 100 is 260. Now I just need to subtract off 78 twice. 260 minus 78 once brings me to 182 minus 78 again. There's 104 degrees left for x. If you check the box that says turn on the midpoints, you can continue to play with them, and they'll draw in the midpoints of that circle back in that GeoGebra. So you have something like this, and they're going to drop in midpoints. And you'll notice that you've got a 90-degree angle on each of them, and that it's cutting it in half. So we can say that that segment is a perpendicular bisector. And the same thing is happening in the other triangle. And as you move them around, you'll notice that the measurements next to them always stay the same. So they are always congruent. So we can conclude that equal chords are equidistant from the center of the circle. So they will always be the same distances from the center, and that line, that distance, is always going to be perpendicular to the chord and cut it in half. So the perpendicular from the center of a circle to a chord is the bisector of the chord. So it splits the chord in half. And two congruent chords in a circle are equidistant from the center. Lastly, anytime you draw in the perpendicular bisector from a chord, so if I drew this one in, as well, it will always pass through the center. Okay? In any circle ever, this happens. So the perpendicular bisector of a chord passes through the center of the circle.